Hello, this is Mr. Collier, and today we're doing trigonometric or sinusoidal functions. So let's take a look at what the graphs of the functions of y equals sine x and y equals cosine x look like. Okay, so I'm going to graph them on the HP prime calculator. Notice these values are going up by 30, so let's type in the functions. Sine x, cosine x. Make sure you're in degree mode, and we can go to shift num, and we can start off with negative 180 and go up in 30s if we put the step size as 30, right? So I'm going to fill in the table first. So I'm going to click on, first I'm going to click on OK, and then I'm going to click on num, and we get all the values that we need. We typed in, just let me double check, we typed in sine and then cosine, so they're in the right order. So it's going to be 0 and negative 1. And then we've got 0.866, negative 0.5. Actually, we have, this is negative 120. So they skipped some in the table. Yeah, negative 120 is negative 0.866 and negative 0.5. Next we've got at negative 90, we got negative 1, 0. And negative 30, we got negative 0.5 and 0.866. So we get the same numbers each time. And it goes up and down, it oscillates. That's why trig functions are so useful. It creates a wave that oscillates like many things in real life. Okay, now I've got it filled out. I'm going to do y equals sine x here, and then y equals cosine x. Let's start in the middle. We have 0, 1 for, we have 0, 0 for sine. And then it goes over 30 degrees, and then we're up at 0.5. And then we're at 0.866. That's getting pretty close to 1. Then we're at 1, then we're back down to the same value again, so I'm going right across from here, so it's very symmetric. As you can see, when we get to 180, we're back to 0, and then we're at 210, negative 0.5, negative 0.5 is right there, and then we're at negative 0. So it's the same kind of numbers. We're getting close to 1, then we hit 1, then we get there, and then we're at 0.5. And then we're back here. And it works the same if you go backwards. So this value is going to be 0.5 down here, negative 0.5, negative 0.866, negative 1. So you get the same shape. So after you get a few dots done, it gets pretty easy. And you get this curve right here. Okay, so this kind of stuff, these kind of graphs happen. And it makes a wave. And similarly with cosine. Cosine at 0, you're going to have cosine equals 1. And then you're going to have the same values. You're going to have at 30 degrees 0.866. So you're going to be up here somewhere. Just kind of an estimate. Then we're at 0.5. And then we're right down to 0, right? 90 degrees, we get 0. And then we go down to negative 0.5. And then negative 0.866. And then we're at negative 1. Then we're back to here. Back to negative 0.5, back to 0. And it keeps going like this, and you can actually continue these graphs forever. It just keeps going up and down like this, like a wave. Okay? Alright, so here is the graph of cosine. So you'll see they're very similar. They're just one is shifted over 90 degrees, right? It's like the sine graph is shifted over 90 degrees. So they're both similar, and whenever we have a wave in real life, we could model it with sine or cosine, and they're both called sinusoidal. Sine x and cosine x are both sinusoidal functions. Okay? But they're very different. Like the sine graph starts at the origin, and cosine starts at 1, or the maximum of the graph. Sometimes it's not 1 if you amplify it. So sometimes cosine is more useful if you start at a maximum or a minimum, as we're going to see later. Okay, so function is useful for modeling many things in real life, like like changes in weather systems and the planets and things like that. They're all cyclical. Anything that's cyclical, we can model it with sine and cosine. Tides go up and down like a sine graph. Okay, tide goes up, then it goes down, up and down. It can be modeled with sinusoidal curves. And a Ferris wheel. So you're at a maximum height, then you come down to a minimum height, then you're back to a maximum. So it's like the height is like a sine or a cosine graph. Okay, so there's lots of applications of it, and we have some specific terminology. Okay, a period is how long it takes for one complete cycle. So for this graph here, the period is, looks like it's 360. Okay, the period here is 360. That's how long it takes for one complete cycle. Here, the whole cycle goes up to 180, so the period is 180. And to calculate, we'll get to that in a second. The period is one complete cycle. The principal axis is max plus min divided by 2. That's like an average. So the principal axis is the thing is the line in the middle. In this case, y equals 0 is the principal axis. Okay, so the principal axis in this case is y equals 0. The amplitude is basically this distance from the principal axis to the maximum or the minimum, which is the same thing in this case. So the amplitude is 1. Okay, so the amplitude in this case is 1. The max is 1, the min is -1, so regular sines and cosines oscillate between -1 and 1. The domain, if you look at the picture, maybe it's a restricted domain, but technically it's all real numbers. The range here, though, is -1 is less than or equal to y, less than or equal to 1. Alright, so if this graph stops here, then we have a restricted domain. Otherwise, it's just all real numbers. Okay, in the second picture, we have a range from -4 to 4. And the domain, let's say it stops here and here, so I'll say 0. It looks like it clearly stops. It didn't clearly stop in the other one. It could keep going, I don't know. Okay, the minimum and the maximum are -4 and 4. Principal axis is again y equals 0. And the amplitude in this case is 4. Okay. Now you got max plus min divided by 2 for the principal axis, but for the amplitude you can do max minus min divided by 2, but your amplitude is always a positive number, so you can stick an absolute value sign on it. We'll be using that a bit later. Okay, so let's check out the amplitude and period of these functions. So they all have a 2 in front. If you graph it, let's see what happens if we graph it. So let's go to apps, function. Let me take that one off and let's stick a 2 in front of here. Okay, and I'm going to change my plot to go from 0 to, I don't know, let's say 360. And the y values, I'm going to go from -3 to 3. Okay, so if you plot it, you can see it, that it goes up to 2. So you stick it, and that makes sense. If you stick a 2 in front, that's like a vertical stretch by a factor of 2, so the amplitude should double. So it's 2 for each of these. Now for the principal axis, it always goes through y equals 0, unless you got a vertical translation up 1 unit like in this one. So this is y equals 1. And let's see what happens when we have 3x. So let's stick a 3 in there. Okay, and plot. So you get, yeah, the period is much smaller now, right? I went to 360, but this looks like it's 360 divided by 3, because now there's 3 full cycles. It was 1 cycle before, so it's 360 divided by 3. The period is 120 for this one. The regular period for the regular function was 360, and this one's also 120 degrees. Okay, so that brings us to an important formula. Period equals 360 divided by the b value. whatever number is multiplied by x. Okay, so you can get the period like over here. You do 360 divided by half, you could actually get 720. And this one's regular. Principal axis is normally y equals 0, but this is shifted down 3, so it's y equals -3. And the amplitude for each one is 0.8.